Okay, so again, this problem 4. What was the point? Okay, the point here was that this is a model of a perfectly elastic collision. So what happens is these two carts come together and the spring gets compressed. And as that happens, the kinetic energy of the carts, so some of the kinetic energy the carts had at the beginning, then gets removed and turned into spring potential energy, or gets converted into spring potential energy, right? So, and then at the end, that goes back into kinetic. So let me maybe see if I can show you something here about what I mean with all this. So erasey. Yeah, there we go. Okay, so and at this point here in the middle, we have, oh, come on. We have both of them moving at U1 plus U2, average of those two. Okay, so if we had sort of a plot of, say, I'm going to plot here energy versus time, okay? So energy on the vertical axis, time on the horizontal axis. What I want to show you here now is that kinetic energy, I'm just going to do kinetic energy in red, okay, is going to start off high, so it's high for this part, you know, and then when they collide, it gets sucked out and turned into spring potential energy. So it goes down. It doesn't go down to zero, generally, unless, you know, U1 and U2 average out to zero. But it goes out to a minimum, and then as the spring expands again and gets restored, it starts doing this. So, and it comes back up to its maximum. Okay, if the spring expands like that. And the other thing to show is potential energy. Okay, so what I'm going to show you is that potential energy starts out at zero. In fact, it's zero up until the spring starts compressing, and then it starts going up, and then down, like that. So that is potential energy from the spring. So what happens there is that the the energy gets transferred from kinetic to potential in the spring, and then it goes back down. So and back into kinetic. So this is a case where energy is conserved, and this is why in elastic collisions we have conservation of kinetic energy, because when we do an elastic collision, we're using the sort of the methods that we like to talk about. We're talking about comparing momentum and kinetic energy here, okay, and here. And so we're sort of using the balance of momentum, or the conservation of momentum, the conservation of kinetic energy, to jump from this point. So this is like you'd call your before point, and this is what you call your after point. And so, and this, your middle is in here. That's the middle diagram. So I wanted to give you the idea that we're sort of, there's this dynamic process in there that involves energy and sort of springiness, even when a perfectly elastic collision doesn't literally use a spring, it still has this springy behavior. So a rubber ball has some springiness to it, and it behaves sort of like a spring in that it stores energy and then releases it by rebounding back to its original shape. So this is how a perfectly elastic collision looks. Now, if we were going to do so you can take just look at this and say this is how a perfectly elastic collision looks. Now, the intent behind part D of this problem is where we say, suppose the ideal spring is replaced by a special spring that behaves the same as an ideal spring while it's being compressed. So what that means is everything up to here stays the same, okay, while the spring is being compressed. And then once the spring reaches its maximum compression, it sticks there. So what happens then is, and I'm just going to sort of show you now instead what happens in the case where we have the condition in part D of the problem, and that is that our spring remains at this thing here, US, and basically never gives the energy back. And so what happens is kinetic energy stays at its minimum. And you'll notice here that this point here, this midpoint here, is where we said the two carts have reached the same velocity, right? Which was the center of mass velocity. And so that's basically where the system stays, because the spring no longer exerts a force. We said that's the special, the special weird spring that we have in Part D. And so what this is here, this is a model of a perfectly inelastic collision. We have kinetic energy, this is kinetic here, is in red, starts off high, and then it gets sucked out by some kind of energy sucker outer, like a, that was descriptive, wasn't it? In this case, we're sort of using this model of a spring that never gives back its energy, but it often is something that crumples or something gets deformed. So the energy goes into basically bending the material, rearranging the molecular bonds, that kind of thing. Crumpling metal, crumpling paper, whatever. Inelastic collisions. So the only thing that really this is not a correct model for inelastic collision, or the only regard in which this is not really a good model, or quite a correct model for an inelastic collision, is that we're calling this this thing that sucks the kinetic energy out, we're calling that a potential energy. And it's not really, because it's not giving it back, right? Potential energy is some mechanism, or potential energy we associate with some mechanism that will give the energy back, a conservative force. And this is not a conservative force here, because the spring does not give the energy back. So it's not proper to call it potential energy. But you can imagine this is sort of the lost energy. In fact, it might often be perfectly correct to call it the thermal energy of the system, which starts off very low but then goes up. So it's actually thermal energy sucking out kinetic energy there in an elastic collision. So hopefully that gives you an inelastic collision. An inelastic collision is thermal energy that sucks it out. Hopefully that gives you some idea of how energy, does things in a collision, and why momentum, and energy work together, or how they work together. Okay, so that is the end of my discussion of problem 4. Ask me if you have more questions.